everyone. My name is Michael Antonov, and here's Volga Aksoy, and we'll be talking about mastering the Oculus SDK. This talk will mostly focus on kind of the C++ aspect of things, and also the general roadmap and where we are heading. So some of the first things we'll cover include just touching on the new SDK features we recently shipped related to DK2, things such as direct-to-rift, driver modes, latency testing, pixel luminance, and so on. And then we'll talk about various techniques and approaches of how to make things more efficient. Also talk about SDK rendering versus app rendering and so on. And finally, we'll talk about some things that can improve the whole thing going forward. So there'll be a discussion of time warp and kind of our near-term and slightly longer-term roadmap on the SDK side. So direct-to-rift. That is before direct mode, and what we had earlier with DK1, we used extended mode for the most time to target the display. So this had a number of implications. First of all is that the rift showed up as an OS display, and it meant that the application had to place the window on the rift monitor. And it had some side effects, such as icons would be in the wrong place, windows would show up on it, and you couldn't really read them easily. And on a more technical, low-level side, it meant also that Windows Compositor was a part of the rendering loop, which led to an extra frame of latency most of the time. Now, latency is something we're always optimizing, so we wanted to get rid of that. So, and finally, we also had to do manual GPU and CPU sync an extra time after present. So with direct-to-rift, we wanted to address these limitations. So as you might already be aware, what happens with direct-to-rift and the new driver is that now display is no longer a part of a desktop, which means it'll just show up in a rift, and you can actually display something else on the window, on the screen. So headset is not seen by the OS. It means it's not going to distract your behavior. There'll be no jumping windows and icons, and we are decoupling the vsync from the Windows Compositor, which means that 75 Hertz or 90 Hertz going forward, all of those rates can be achieved without any kind of slowdowns or delays. So another thing is we can avoid extra GPU buffering by taking advantage of kind of a low-level driver kernel interactions. So from a programming point of view, the way you use a rendering mode is set up a regular window with a swap chain, and you call something, a function called attached to window, and from that point on, an output will actually show up on your rift. And this is really fairly straightforward to use. Now, we do hope that direct mode will become, as we work through various kinks with it, will become more of an accepted and standard solution, since it allows kind of seamless switches between applications and various other things. So another feature which you're aware of is that it allows mirroring. So you can display a duplicate of the image in your window. Now, there's a few nice things about that. One is that the window actually does not need to be the same size as the rift, and it can actually display a different image. So in our world demo example, the white text you see up there rendering to the rift, it's actually a child window overlay. So what you could do is actually put something else in there, and it may be like a single-person view or some kind of a summary screen, which would be useful for an observer without stereo. So mirroring has minimal overhead, but it does have some CPU implications. So you can turn it off if you want to. And of course, you still need to worry about focus and input going to that window, because that's how things work. And I've talked about being able to display a different image on whatever you want. In terms of implementation, I just wanted to touch on some of the things. We are actually involved with different parts of the DirectX stack, and we do plan to adding this type of functionality in other OSs as well. And we're working with, to try to minimize that impact, because we prefer not to write low-level drivers if we don't have to. But what it does is several things. We shim a Direct3D and OpenGL runtime on the user level, which means that when you create a window or a swap chain, we know about it and we can do something else with it. It does mean on a technical level that you need to initialize the rendering ship or LIDOVR before we start. And whenever that happens, the swap chain of a window will automatically show up on a Rift primary monitor. So now another thing is, since DK2 uses a portrait display, we actually rotate the image as it gets copied to the primary scanned out buffer. So that's one of those things which we virtualize to make things simple. We do recommend that the resolution which is rendered is the one which comes from SDK, even if you can actually create different buffer sizes. So another part which we shim is really the kernel level and kind of a low-level OS stack. And this is what we really needed to do to prevent it from showing up on the monitor. So here, it hides the Rift, and it only shows up within our software. And it also enables efficient vsync, which I mentioned earlier. So now there have been a few technical details, so I wanted to thank everyone for bearing with us as we rolled this out. There's been a number of things that we needed to resolve. So there's been a number of symptoms, so I wanted to touch on those and kind of let you guys know how we are working on addressing those. So the most common thing was the Rift simply did not turn it on for some people. There's been a number of reasons why that is. Most commonly, it happened on multi-GPU systems. And that relates to both mobile, where you have Optimus, which is dedicated plus Intel hardware, and it also happens sometimes on SLI configurations. So the tricky thing here is we found that on many laptops, the discrete GPU is not connected to the HDMI port. So which means that you have to route the data through the software, which incurs latency and processing, and that logic basically just has to be there. So we're working through optimizing that area and creating a bridge. Actually, if you look at some of the NVIDIA technologies, and what they did is Optimus actually implemented their own bridge in Windows 7 and 8, and Windows 8.1 comes with adapter support. So we are working to kind of virtualize all that so that no matter what the case is, we handle it correctly. So we've been able to get some promising results. So for example, some Optimus systems, such as Razer Blade laptop, happens to work very well. Well, we've seen some other laptops where, for some reason, just copying that one frame takes 10 milliseconds. You don't have a lot of time to render after that, no matter how fast your discrete GPU is. So, that's something which hopefully will not happen too much. So, and in terms of the multi-GPU crossfire configurations, those should generally be usable, but one trick is when the video is plugged into the wrong adapter, which is not the one which has a frame buffer, again, the copy is needed. And our software would not detect that, and we're working on resolving those issues. So there have been a few other things which made it tricky. DisplayLink is kind of an adapter which makes monitors work with USB. They also shim the kernel, so they've been conflicting with us. So we're working to resolve those issues. We don't actually expect to ever be able to use DisplayLink for the Rift, but hopefully it won't be conflicting. And there have been a number of issues with multi-monitors. So if you have several monitors on a desktop, what the OS does is actually sometimes try to sync them together, or it syncs all of the output to the frame rate of a monitor. So we need to decouple it. And all of that actually should be addressed in an upcoming driver update. And some other shims. So if you guys encounter these issues, please report them. We'll be categorizing. And I suspect that within the next 2 to 3 months, we'll be able to address most of these. It'll be hard to get perfection, but the top items, I believe, would make most people happy. So what are some of the things we're working on that? A lot of effort is, and kind of forward thinking, going about distortion and composition kind of in a separate process. What we'd like to do is actually be able to combine overlays from maybe some of our software stack with a game and do things like time warp separately, and all automatically without delays and glitches. And we'll talk a bit more about that later. And if we were to separate that logic into a separate process, it would make developers' life simpler. It would remove shims from applications, which means you wouldn't, if there's any kind of issue with devices and so on, they wouldn't show up. It would simplify state management. There have been a number of bugs and things which were when we didn't restore some state or developers weren't aware something was going on. And it would support time warp layers, which we'll talk a bit about. And of course, hopefully the asynchronous time warp. And there's a few other things which haven't, like one of the toughest areas is really mobile. Like if you look at the laptop, how can we take advantage of that power? So that's usually when you don't have enough fill rate. So one of the areas we are looking at is actually trying to use both discrete and built-in GPUs together. So with Optimus, for example, we may be able to do time warp and distortion on the Intel GPU while combining that with a discrete card. Those types of optimizations will get things to be better over next few months. And we're always researching better GPU pipelining and preemption. That is, things which make it more efficient. So I'll now hand over to Volgar, and I'll come back to talk about time warp and things a bit later.
Thanks, Mike. All right, so I will be talking a little bit about some of the newer SDK features as well, and then we'll move on to some other topics. So at Oculus, we've been talking quite a bit about the notion of motion to photon latency. And essentially what it means is basically from the point the user starts moving their head, you're sampling the head-mounted display, that feeds into your rendering, and then the rendered scene eventually makes it onto the screen, and the screen finally lights up and physically shows the user what's happening. And the delay in that is essentially the motion to photon latency. Now, keeping that latency low is obviously really crucial for a solid VR experience. And at Oculus, our goal has always been to make sure that that is roughly less than 20 milliseconds. And hopefully, the closer you can get to, say, 5 milliseconds, even better. And the good news is actually on the PC side, we're getting really close to this point, and we'll be sharing some of our numbers in a bit. When you look at the DK1, the way you would do latency testing was by owning this piece of hardware that was purpose-built by Oculus. You would essentially screw it into the lens cap, and when you push the button, the application would essentially go into a latency testing mode. And you couldn't really interact with the application at that point. It was basically not usable, and you had to wait for the results to come back, and you would just see the results, and that was it. And ultimately, that was basically too cumbersome. Very few people utilized it, and that meant that there was really minimal developer utilization. Wasn't too surprising. With the DK2, however, we have some new cool features built into it. Essentially, the panel of the DK2 can sample the top right pixel, the color of the top right pixel, and it also knows exactly the timestamp of when that color changed. And it can reroute that information through the USB to the PC, and then the SDK ends up taking over the rest of the calculation to orchestrate the latency calculation aspect. The interesting part here is that the SDK internally can utilize the very accurate CPU and GPU timing to know exactly how many milliseconds have passed up to the point where your application is calling present. Unfortunately, from that point on, it becomes a bit of a black box to the VR application because there is, at that point, the VR app has no idea how many milliseconds it's going to take for that information to finally hit the screen. And that's the part where the SDK relies on the DK2 latency testing feature. And the reason why this is a bit of a black box is because there's a whole slew of different things that you have on PCs that can ultimately change the behavior of how the timing ends up responding. and the OS, the GPU. We've seen all of these alter that timing. And at Oculus internally, we've seen that it can go anywhere from 0 frames, maybe all the way up to 4 frames and above. And when you consider that for the DK2, that essentially means at 75 hertz, you already have potentially more than 50 milliseconds. And obviously, you want to make sure you're accounting for that somehow, or you at least know about it up front. So the high-level implementation of how this latency testing feature works is basically that the PC side renders to the top right pixel a certain color and records the time of when that was rendered. And then once that reaches the HMD screen, the HMD detects that color and sends back the PC when that certain color was detected. Then the SDK takes that information and matches it up with what it originally recorded and when that came back. And the more samples it takes, the more reliable it gets, and eventually it starts reporting very accurate latency times. So the final latency calculation, however, ends up being the time difference from when the HMD was sampled just before present up to the point where the DK, and that is included to the point where the DK2 latency testing ends up returning a value, and it's basically the summation of those two values. Now, if the latency testing feature fails for any reason, and I'm going to go into why it might fail, the SDK eventually falls back to a best guess value. And that really depends on the kind of headset you're using, obviously. For example, in the DK1, since we don't have that value, it always ends up going off of the best guess value. The latency info is ultimately also available to the application. It's not only there in the SDK, and you can also see this in our Oculus World demo. If you hit space, you'll essentially get this kind of info on the screen, which has a whole bunch of VR-related info, and I'll go into that detail of what each of them mean. I should note that sometimes you'll see not applicable show up instead of the timing, and that can happen due to various reasons. For example, perhaps your application isn't properly full screened on the HMD, so the top right pixel isn't getting rendered exactly where it's supposed to. Or maybe you're not running your application V-synced, so the timing, the colors, the top right pixel color might not be going through the transition of what the SDK is expecting because it's flipping way faster or way slower than expected. And maybe if you're trying to do this yourself and you have incorrect gamma space, then again, the colors might not be going through their expected values. So these are some of the reasons that you've got to make sure that you've nailed down before getting the latency tester feature to keep working reliably. Here in this case, you'll see the REN section in the world demo, and that effectively is the latency from the point the HMD sample pose was sampled to the point it was eventually rendered. And then for time TWRP, this is essentially where time warp is executing, and that ends up being the end frame call in the SDK. And essentially, that is the point the time warp feature has sampled the HMD again to the point it actually made it onto the screen. And the post-present one is the one that we were just talking about, where it is that black box timing bit that can vary depending on the configuration. This particular shot, I captured that on a MacBook Pro with GeForce GT 780M, and it was running Windows 8.1. And in this case, our post-present latency is 0 milliseconds, and time warp roughly lands around 7 milliseconds. If you consider that the screen is scanning out from right to left, that essentially means that the midpoint of the scan out lands around 10 milliseconds from the point it was originally sampled. And and in this case, we do have 0 millisecond post-present because we've actually now started saving that. What we used to see with that 1 frame latency in direct mode, we can now save that. In extended mode, however, if you're running it that way, you'll still see that 13.3 millisecond latency show up with the DK2. And the larger the post-present gets, those values will eventually feed in and increase also the REN and TWRP sections as well. So now that we know accurately the motion to photon latency in the SDK, then what do we do with it? Well, in the Point2 SDK, it was up to the game developer or the application developer to feed in a prediction value and hope that they got it right and relatively accurate. Well, that's where this new idea of dynamic prediction comes into play. Essentially, with the DK2, because the SDK internally knows the latency, it can directly feed that straight in as a prediction value for your head-mounted display sampling, because it becomes kind of a closed loop in the system with the SDK and HMD interacting back and forth. So the VR application no longer needs to worry about this number. And ultimately, that's a huge win on the quality of VR experience you're going to get. So one of the artifacts that have been discussed previously is this artifact on the DK2 screen that's called 2-frame rise delay. Essentially, what's going on there is that the display isn't hitting the requested values as quickly as you would expect. And by that very notion, it takes usually exactly 2 frames. And we're accounting for this in the SDK with our software CPU and GPU utilization. So if we were to show kind of what's going on under the hood, say on the left side is the case where we're not doing anything special, it's just operating as normal. And you'll see that the jagged line is our requested colors, and the dashed blue line is what the DK2 screen response is doing. And you'll see on the first frame, it's getting relatively close to the requested color, but it's still not hitting it until we get to the second color. So knowing that gap on the first frame of how much it took to potentially get to the color, we can essentially feed in an overdriven color that makes the screen end up having a steeper curve and eventually hit that color on the first frame. Now, in our shader, this is basically implemented with a relatively similar code as shown, and basically we're applying an overdrive scale, where in this case the overdrive scale roughly is about 10% when the colors are rising and 5% when the colors are going down. And this is currently implemented in DX 10 and 11, and we'll be bringing it over to OpenGL and D3D real soon as well. The interesting part about this is that because the SDK needs to know exactly what the DK2 screen is showing for the previous frame, it needs to basically run in VSync. Otherwise, the GPU won't have any clue what the screen is currently showing, because in that sense, they won't be synchronized anymore. So that is essentially yet another reason why you always want to make sure you're running with VSync enabled. The 2-frame rise does fix a lot of concerns that people had in the past. For example, in the world demo, if you are standing in the cottage and you're looking out through the window, you'll notice how the frame of the window might blur onto the sky and vice versa. Or if you look at the cypress trees, they would have this kind of ghosting artifact going on onto the sky. It does fix those, but it doesn't fix the staircase and the fireplace that has this really black smeary artifact that a lot of people have been referring to. So that's basically an interesting anomalous behavior in the response curve of these screens. And I think Carmack had briefly alluded to that as well. And essentially what's going on is with the DK2 screen specifically, this artifact is happening only on the green channel. And it's only where you're going from extremely dark green values, say out of 255, maybe from 2 or 5 or 10, and you're going to still relatively dark green colors. And the way we are looking into fixing this right now is by fine-tuning and evaluating every color transition to create a nicely tuned lookup table. And essentially, that's going to feed in to the shader that I was just showing you as scale values that are determined per new and previous color transitions. So next, we'll go into some real-time engine integration tips. And we'll be hitting some of these at a high level. And let's go straight into it. So with the Point2 SDK, we didn't really do any rendering on the SDK side. All the SDK did was just provide you some parameters in the hopes that you would query them the right way and utilize them in your own rendering path. With the Point4 SDK, however, we have a whole new rendering backend, and it takes over a lot of the critical stuff that gives you a really solid VR experience. all it requires from the game developer is to make sure that you're properly rendering a left and a right eye image with the right projection, and you feed them into the end frame function. And from that point on, the SDK continues down the path to the present call and applies a lot of these bullet point features of the ones also we've talked about, making sure the latency is low, we're doing the right kind of overdrive and the chromatic aberration. So you don't need to worry if you're rendering on a DK1 or DK2 or something. Hopefully that would be coming down the line. So our goal with the SDK rendering path is to make sure that every engine will be able to use it. And we should also preface that by saying that Unity 3D and Unreal 4, they're both using the SDK rendering path. And that's also why we have our SDK rendering code open sourced, and we definitely encourage that you take a look at it, see if there's maybe any deficiencies. And in the case that you believe that the SDK rendering path is something that you cannot utilize, definitely let us know and tell us why you can't use it, because that is the way we will make sure that we're crafting an SDK rendering path that will hopefully solve your needs. That said, there are some valid reasons why you might not be able to utilize it, and we might not be able to do much about it. Say you don't have your engine source code, so you simply can't integrate the SDK into it, but you're just a content creator. Or maybe you're utilizing some render API that isn't public. We wouldn't be able to ship with that API support either. Now, interestingly enough, there's some techniques that developers might think isn't applicable, like the case of the stereo 3D post effects reprojection technique CryEngine does. In reality, that is something that would work, but again, these are the kind of things that we need to create a dialogue with you guys to make sure that this is accounted for. Maybe you want to do some post-distortion rendering, like maybe you want to render some debug text on the screen after the time the distortion has been done. Maybe you want to watermark the frame buffer. That is something we don't currently support, but if there's a need for it, again, let us know. And maybe there's some showstopper bugs that we're not aware of. Maybe there's flat out missing features. And these are all the things that, you know, we would, as usual, just let us know. And I'm trying to harp on this point because we've seen a lot of developers that kind of just turn off the SDK rendering path, assuming that there's no way they're going to be able to get those features. And this is something that we would like to create a dialogue with developers for. So the recommended SDK integration path goes along the lines of initially just taking the Oculus Room Tiny. And mind you, this is not if obviously you're using a supported engine, but if you're putting it into your own engine for the first time. You want to basically look at the Oculus Room Tiny, see how it's bootstrapping the SDK. In that sample, we show how you can achieve both SDK rendering path as well as app rendering. Once you know everything there is good to go, you have a solid VR experience, then you can move on to the Oculus World demo and look for some of the more advanced features. And those are essentially all laid out in our options menu when you hit the tab button. Judder is one of those things that have come up time and time again, especially when you talk about the DK2. Interestingly enough, this wasn't really brought up that much with the DK1 users, partly because the DK1 had a relatively smeary screen, it didn't have the low persistence, and it wasn't as accurate as the DK2. When you look at the DK2, for example, the low persistence, the higher resolution, the precise tracking, these all essentially created a very finely tuned, accurate environment. And any kind of hitch would almost have this uncanny valley of VR tracking. The closer you get to creating a really seamless experience, any little twitching or any little inaccuracy ends up pulling you right out of it, and it becomes a more annoying feature, annoying experience. So some of the more obvious reasons on why this is happening, for example, obviously low experience, right? Low FPS. Maybe you're throwing way too much at the GPU and the CPU, and the end user's computer can't handle it. One of the more obvious ways of doing this, right now, maybe you're not thinking too much about this, but down the line, if you want a wide array of people to be able to play your game or your VR experience, you got to make sure you're putting in a lot of graphics options. This is kind of something that a lot of AAA game developers have already been used to in the PC department, but you have to make sure that you're also accounting for this, especially more so for VR games, because dropping frames simply isn't acceptable. And then you might have highly variable prediction. If you have very unpredictable frame loads, maybe one frame it's trying to predict 2 milliseconds, the next frame is trying to predict 10 milliseconds, that kind of really disparate predictions can make it look like it's actually having dropped frames. In fact, it might just be overshooting and undershooting. Ideally, Time Warp takes care of this, but there's situations where it might not be able to. And then sometimes this is an issue with end users where they have an incorrect setup, where maybe you have a bad refresh rate simply because even though you think the application is properly running on the screen, at full screen, maybe it's accidentally running in a window, or it's running in this quote-unquote fake full screen mode because maybe it's trying to do some debug trickery. There you want to make sure that the application is properly full screen, because otherwise it's going to accidentally V-sync with a different screen, and usually that ends up being the primary screen. Or your engine might simply be incorrectly using the timing accuracies of the SDK, and we'll touch on that in a little bit. So one of the things the SDK provides is the recommended eye texture resolutions. And you can change this value on the fly if you want to, and simply push those values into the end frame. The rest of that pipe ends up being taken care of by the SDK. With the distortion, all the values are internally updated properly. And one good reason for doing this is perhaps knowing that you're not going to be able to maintain the high frame rate where the situation is changing dynamically, so you dynamically also scale down your eye resolutions. This is something you can also see in the Oculus World demo, and the option is in the dynamic res scaling, and you'll notice that as it's scaling up and down the 3D scene, you won't be able to tell exactly that the 3D scene resolution is going down. Where it becomes really obvious is for the UI, because the text granularity, again, something that Carmack was trying to harp on, the text legibility becomes a serious concern when you're dealing with these kinds of things. And ideally, to account for this kind of thing, you would have a split layer behavior where the 3D scene might actually be lower to a lower res buffer than the UI. This is something we don't currently support, but Mike will talk briefly about potentially bringing that kind of support. So the SDK also provides you recommended FOVs. And FOV in this case is 4 separate values of tangent angles for each direction in the camera frustum. And we also have helpers to make sure that out of that FOV port, you can pull out a regular projection matrix. One thing we want to harp on is that please don't try to cook up your own projection matrix, because we've seen a lot of times where people think they eyeball it. They're like, yeah, I think that's good enough, when in fact, sometimes we've seen games that have divergent stereo parallax. That is a no-no when it comes to stereo rendering. But we've seen it, and people have thought that that was the right way to render it. So you can change your FOV based on your game's needs, but in this case what you're changing is what we could call the virtual FOV, because the head-mounted display's physical FOV doesn't really change. And you end up passing those values into configure rendering, and the SDK under the hood will regenerate your distortion mesh. And again, just like the texture resolution, the SDK internally takes care of the rest of the modifications. That said, because an FOV change causes the mesh to be regenerated, we actually don't recommend that you change this FOV every frame. So in the world demo, we again have the feature of changing the FOV on the fly. And if you look at head-mounted displays, like I was alluding to, there is a physical FOV, and unlike regular monitors, you don't want to keep changing this. And ideally, your virtual FOV should never really grow above and beyond the physical FOV. And if you modify your FOV, essentially it should respect the physical FOV of the screen. And you can see in this screenshot that it didn't bulge out the view like you would expect in a classic FPS. Otherwise, you would get what could be perceived as some kind of weird binoculars effect. And while you might want a zooming feature, this wouldn't be the right way to implement it anyway. So why do we have 4 separate values for the FOV? It's partly because we have different values for each of them, because the inner FOV, for example, doesn't match the outer FOV. As you can see in this image, in real life, your nose actually does limit how much you can see on the inner side of your head. And we're trying to make sure that we're utilizing the maximum screen space on the head-mounted display to create the maximum amount of FOV on your horizontal plane. And interestingly enough, the DK1 actually had more asymmetry than the DK2. And that's where the asymmetric frustums come into play. So I'll briefly talk about that. In some engines, they're written in a way where they always expect symmetric frustums. And this is kind of understandable because asymmetric frustums usually only really come up in practical cases of doing stereo 3D rendering. And you can fix many of the subcomponents, but sometimes they can prove to be too cumbersome, especially if you're trying to go through millions of lines of code. And perhaps your camera framework system only accepts symmetric FOVs. We've seen artifacts of deferred shading pipelines where they don't properly interpolate across the frame buffer when it's an asymmetric frustum. Culling might not be handling it properly, and a bunch more problems. So essentially, the easy way to fix this is to make your FOVs symmetric. Essentially, the way to go about doing this, and you can also see this in the Oculus World demo, is to make sure that you're taking the maximum of the inner and the outer FOVs. And notice in the image currently, they're asymmetric. And once you make them the maximum, you avoid that artifact, and you get the result of the rendering will, even though the result is a symmetric rendered buffer, if you clip it properly, the result will look like just like it was asymmetrically rendered. Now the problem here is that you're essentially wasting a little bit of buffer space that you've rendered at that point. And if you start to notice maybe that's becoming a performance issue, we'd highly recommend that you apply a scissor before you start rendering the 3D scene so that that eventually clipped out area doesn't actually take any performance hit. So we realize that, trying to cull a whole bunch of stuff and maintain high frame rate, it can get expensive, especially if you have to cull once for each eye of the head-mounted display camera. So some engines just go, you know what, I'm not going to worry about it. Just take the center camera view and just cull once and live with the sliver artifacts that might show up on the sides. And that's where a unionized camera effect would come into play. Essentially, you're creating this frustum that would account for both the camera frustum spaces. We currently don't support this, but if anybody here feels like that is something that would prove helpful to them, definitely let us know. We'd be more than happy to get that into the SDK. And essentially what it would look like is it would take in 2 camera transforms and 2 projections and return you a single transform and single projection. That would be the unionized camera. So another part I'll talk about is the idea of split versus shared eye textures. Our SDK allows you to go either way, and in that case, if you decide one way or another, you can let the SDK know about your intentions by setting the viewport and sending that through the OVRI render description that you pass in. And in the Oculus World demo, you can see how this operates under the hood. We have that as the shared render target option. Obviously, it's not interesting to just look at visually what it looks like, because ideally it'll just look the same. You want to actually look into the code and see how it's doing things differently. So the reason why we bring this up is because there are pros and cons to going about both ways. When you're doing a combined eye texture, for example, and this is also the way Unreal 4 does it, every draw call, you can alternate your render targets alternate your eye buffers without modifying your render target. And essentially, you can get, in a sense, more bang for the buck with your draw calls without having to upload new material constants or anything like that, because you can just assign one material and plop that geometry on both eyes, one after another. And that would be the upside. And another one is possibly doing a post effect. After you've finished rendering both of your eyes, you can render a single quad instead of one for each eye, where you do your post effect in one sweep. When you go down the split eye texture method, though, there are some upsides to that as well. For example, you have a relatively distinct midway point in your frame buffer, and that can help with some of the stuff that we're internally looking at, particularly with workload balancing your time warp. Another useful thing is the fact that now your eye textures overall end up being smaller, and some GPUs function faster this way. And another interesting part is that if you have different eye relief for each eye, and this is a relatively common case, then you can resize your eye buffers to be different without wasting any render target space. One of the most important pros for this method, though, is the fact that when Time Warp is trying to correct for a lot of panoramic shift, so to speak, you don't accidentally bleed from one eye sampling into the other, where you might have to otherwise in your distortion shader and Time Warp specifically account for that to make sure you're clamping across the border. And when you split the eye textures, this becomes a non-issue. So the last point we'll talk about on this engine integration is the fact that some engines are dealing with timing when they're inherently multi-threaded. So one of the first things that engines do is sampling the input devices, and then they take that the sampled input and send it into all of the respective systems like physics and AI and whatnot. And you can think of the head-mounted display as also yet another input device. And when in the past, we've seen a lot of engines with multiple threads have frame input latencies over 2 frames. And that's partly because they never had to worry about head-mounted displays. Controller inputs above 2 frame latencies were actually kind of okay. And if you look at that from a strictly millisecond latency point of view, right off the bat, if you don't account for it, you would be adding more than 25 milliseconds latency. And this is where Time Warp again comes into play. You want to make sure you're absolutely using Time Warp to decrease your latency, but that's not the only trick. So when you look at a classic 2-thread engine where it has like this producer-consumer model, and the main thread is generating the simulation data, passing it over to the render thread, and the render thread eventually sends it off to the GPU. On the main thread, you want to make sure that the main thread is doing all the thread-safe calling only the thread-safe functions that go into sampling the head-mounted display pose. And essentially what that comes down to in our SDK specifically is that you're calling get frame timing, and that gives you the values that you can send into get tracking state. And another new call we're bringing into the API soon is this new get eye poses function. Essentially what it's going to do is it's still going to return you the center eye pose as well as the left and the right eye poses. And you won't have to worry about accounting for the center eye to head mounted, the center of the head mounted display to the eye offset. It'll be handled automatically. And the cool part here is that you can also use this function without really worrying too much about it on both the main thread and reuse it on the render thread. So the 0.4 SDK Time Warp feature mainly just fixes your orientation latency. Now this is fairly good in the sense that the majority of the lag feeling actually comes from orientation lagging, but there is a tiny bit that could come from positional latency. And the way to make sure you're accounting for that is to go and resample your head-mounted display pose just before you begin rendering the 3D scene. It won't be obviously as low latency as your orientation correction, but it will be much better than just doing it on the main thread and never worrying about it again. And in this case, you want to make sure your Time Warp is getting very precise timing triggers. And essentially what we mean by that is you're starting it with your begin frame or begin frame timing on the render thread, and you're ending with your end frame or end frame timing calls. And in our SDK, there is really no other call that affects the timing that eventually feeds into the Time Warp each frame. Now, the parameters that get sent to the Time Warp are all basically going into your end frame call. And essentially, those are simply your 2 render poses, 1 for each eye, and the 2 textures, again, 1 for each eye. Although you can, like I was pointing out before, you can share those textures for each eye. The most important thing I should point out about this, though, is that Time Warp in itself does not care at what point the head-mounted display was sampled prior to Time Warp or via what SDK call that render pose was generated. As long as you're providing the render poses that were genuinely used for creating those eye textures, Time Warp will be able to account for that. And you can, for example, get those to, like I was just pointing out, the poses from get tracking state or the get eye pose functions. And on that note, I'll leave the rest of it up to Mike.
Thank you, Volga. So in terms of time warp, we talked quite a bit about it. I think a dancing version might be easier. But in terms of what it does, you guys are already familiar. It reprojects a rendering to a point, a later point in time where the sensor is going to be. And it's done actually simultaneously with distortion, so it doesn't have an occurred coast. Mostly we are using it to reduce latency, and another thing it does is actually account for rolling shutter, which is this beam of light which crosses the screen at different points in time. So there's actually transformations done on the right side, on the left side are slightly different. So as Volga mentioned, we handle currently orientation, which is the biggest visual cue, but it is possible to do some positional time warp. And in fact, in our SDK, if you look at the shaders, we have a research implementation available. So you have to provide a depth buffer, it gets a bit involved, and it's something which could help, especially once you have positional tracking. Now, so far what we have been doing is synchronous time warp. And that's really when we are rendering at the same time, just within that same frame. So we draw both eyes and then we distort those eyes based on a later sensor reading. And the biggest issue with that is if we don't hit the frame rate, we get jitter. And that's really been the most challenging thing about DK2. It's mostly because as your eye rotates, you're getting the second image. So it's not that necessarily our prediction is wrong or something else, but if you skip a frame at all, you'll get that effect. So, and this is much worse than it would be on regular monitors. So you need to do everything possible to address it. It's actually, so the question becomes, can we actually use time warp to reproject and generate intermediate frames when they're not there? If our game, for example, is going at part of the speed. So philosophically, the answer is yes. Now, there's going to be some side effects to that. So you cannot fill in data when it's not there. So you can, even if we get it done right, if you're moving side to side next to a nearby object, that depth data is, occlusion data is not there. So you will see some trails. But it can be done. So an example of that actually is available in our world demo. If you press the C key and you look around, you will see that you can look at the scene without it actually being rendered every frame. So the rest of the scene is filled in with black there, so you can actually turn quite a bit. Now, missing scenery turns black, and an interesting thing is that UI actually moves with the image. Now this is actually undesirable, and we can talk about that a bit later. So the question is, asynchronous time warp. First of all, why haven't we done it, and how could it work? So the thing about asynchronous is obviously it has to be on another thread. So what you really want is something which can do rendering in time with vsync. And it's really our best hope to reduce jitter. Now, we've implemented that on Android in Gear VR, and it actually works very well. That is what allows many Unity experiences to work, and it really fills in the frames pretty well. Now, it does work slightly better on without positional tracking, simply because with orientation only changes, you don't get any lost data. Now, there's a couple of things that actually that requires. It requires priorities and GPU preemption. So what you want to really do is be able to stop your rendering if it's taken too long and produce the result. So here I'll kind of briefly illustrate a diagram of how we might want this to work. So on this image, we have several frames. And what we are doing is submitting left and right data. And there are several threads. So the first thread is the CPU rendering thread, which is submitting rendering commands. And the second CPU thread would be the time warp thread. That's the thread we'd like to have kind of higher priority. And it's going to submit a time warp call shortly before each end frame. So what happens is that the GPU command processor is going to process all of the data. So it's going to do left and then right. As what you can actually see in frame N, here is that the right eye isn't completely finished when we get the time warp render to come in. This is what you'd like to happen. Now, if you couldn't make it? Now, ideal scenario, you make it to actually get all the frames and the best latency. So if this was to happen, what we actually would do is take data from the prior frames. You do want to take it from both sides. If you try to alternate and do it one at a time, you'd get mismatching timing. So, and of course, if we did that, we'd be able to continue rendering later on, and it's your kind of basic preemption. So the question is, why haven't we shipped this on PC, and what are the challenges? The most basic thing is current OSs on Windows do not provide techniques for fine-grained GPU preemption. And there's no notion of GPU priorities that is exposed to the user. So that's kind of the biggest area that we're working through. So we're working with GPU vendors, and we are optimistic this functionality will really be coming soon. So already, AMD, for example, supports the compute shaders preempting the regular rendering execution, and NVIDIA does provide some priorities internally. So it's really a matter of exposing it, proving it, and making sure the code can really be portable all across. So besides having this functionality, we're also exploring different adaptive and cooperative ways. So one way you can look at it is, instead of doing real preemption, if it doesn't work, you can actually try to generate one extra frame if on our driver level we allow you to submit predicted frames. So then if you don't quite make it, you'd get the prior prediction, which is better, instead of a more recent kind of higher precision image. And then you just catch up. That would allow you to have spikes in CPU timing and in rendering, which are filled in. So those are the type of things which we are looking at now. Now, one interesting thing which happens with time warp is if you actually try to apply it to the whole scene, you'll notice that it doesn't, you actually want to have multiple transformations for different objects. So a good example is world space and cockpits and UIs. So what you kind of want is to have layers. An example of this is, let's say you're in a cockpit in a car. Now the car has a velocity through space, but your translation within a cockpit needs to be mapped directly to the physical space. This means that now on a car, if you just fill in and you generate the same transformation, the velocity of an outside world will not be included in that particular piece of time, so you'll get jitter or motion stutter on the outside of a frame. So what you'd like to do is really add the timing and velocity to the outside world while you don't do that in a cockpit. So the way to do it is really to have multiple layers which you combine. So what you might want to do is really also feed in control of input. So if you have a first-person shooter when you're moving through the world and you have rotation or transformation, you may want to be able to add that transformation into the time warp to get smoother results as you go. And finally, for UI layers. So as you could saw the user interface, you really want it to be located in a physical space next to you, so you don't want to transform it, and if you do, you'd get stuttering. So again, that's a reason to, in the future, we expect the blending to be a multi-layered effect. So the solution for this is really having a shader and a set of tools, and our future SDK will expose layers which will let you do that. Right now, if you do go with game engine rendering, so if you choose to modify our code and work with it, you can combine and implement these kind of techniques. So we've seen it help in cockpit games and space simulators. So I'll briefly go over some of the things which we are going, and it's already in terms of a roadmap. So our current So basically, short term is can't really commit to any particular date, but over the next 2 to 3 months, we hope to address these things. And the biggest thing is driver improvement in fixes. We'd like to fix the multi-monitor jitter, and actually, that's pretty much done. It'll be coming out soon. So this is when some of part of jitter and timing issues were caused by monitor syncing. Reduce post-present latency, and as you saw, Volga had a 0 post-present number. That's also will be coming with a new driver. Address multi-GPU and Optimus scenarios. Now, of course, we are working on being cross-platform, so Linux support will be coming soon. And we are really working hard on addressing the jitter through adaptive synchronous time warps. Now, the thing about this is we really do prefer our games to run at full frame rate because there are visual costs even to being able to fill in the frames. But at least this should help quite a bit, especially on mobile systems. And time warp layers, which I talked about. Now, kind of slightly longer term, we are looking at really making runtime DLL, which would allow us to scale to future hardware. So let's say we look at Crescent Bay and we introduced back-of-the-head tracking. If we change the refresh rate and other details of the screen and lenses, the best way for us to do that is to be able to supply a DLL, which would allow games to update to that automatically without having to rebuild and recompile. So we'd like to, within kind of a longer 2 to 6 months time frame, we'll be switching to that model. It does mean there'll be less frequent versioning, but hopefully kind of more functionality will be released in those. And the other thing we're looking for doing is advanced VR composition. And I've touched it on that barely in terms of potentially having a separate process which does all the blending and time warp. This is where you can submit textures and they're fully handled by a pipeline. And one of the advantages of doing it in a separate process is, besides the state management, is that you can do better preemption and better timing control. And we can inject things like safety warning and languages for that and other overlays without that actually having to reside in your game code. So, and of course, we're looking at audio. There'll be a great talk by Brian Hook later today, which will be discussing like spatialized audio and research we're doing in that area. So we're hoping to add and extend things there. So that's pretty much it. Now we'll open for any questions you have about SDK. All right. Direct rendering on macOS. It's actually one of the trickier ones. Well, our macOS guy does have a plan for that. Can't say a definite time, but I suspect, I'd hope it's within like 3 months or so.
Runtime, DLL, when you switch to that, what's the policy going to be for backwards compatibility?
So we definitely need to take that seriously, so we are thinking about it a lot. At this point, we are careful about not making as much of a break-in changes, or if we do, there'll be a period, and before the consumer release, there'd be a period where we deprecate potentially something, release a new version, and maybe within a month or 2, we can choose to remove new functionality. But kind of going forward longer, it may be that we try to make it compatible, but if there is some new hardware which comes out, we can choose just not to update the older versions at some point selectively based on what can be done. Go ahead.
I don't know if this is working. Is it? Yes, okay. How much crossover is there between the work that you're doing with the SDK for Linux here versus the Linux on mobile devices? Is there any crosstalk? Is there anything that you guys are focusing on specifically?
They are very different systems. So mobile is an Android system, and some of the internal sensor fusion logic is shared, but there's a lot of Android custom driver optimizations, which are only available on Android, and CPU and GPU scheduling. The PC and Linux are actually more similar in that sense, and Mac as well.
Is the Oculus SDK going to be sort of the glide of VR APIs, or are you guys looking at any open standards?
At the current point, our goal is to support our devices because I actually, there's not a whole range of devices, and other ones are not necessarily open. I suspect longer term, there'll be APIs and things which come up. But right now, having it kind of the way it is allows us to iterate and move fast and kind of address a different hardware situations. So at some point, yes.
For time warp prediction, does it adapt to each user or is more generic when you do the prediction?
So there is several things. So if you have, let's say you have asynchronous time warp, it will generate frames just before the vsync scan out. So or as John was talking, you'd preferably do it even as you raise the beam. But assume that you don't raise the beam, it would be just before that time. Now, if you happen to not have a new frame, it takes the prior frame's orientation and computes the data on it. If you miss 2 frames, it would still work. So it actually works to fill it in, but of course the quality very quickly degrades. Now, the other thing it does is work with prediction. Whenever you generate any new frame, you need to target your time to specifically that point. So that math plays a role as well. So I don't know if that answers your question.
No, actually. The prediction is based upon multiple samples of users using the system, or is it based on each individual user?
Prediction is based simply by adding extra time to the sensor, essentially velocity and rotation velocity. So it's a very simple calculation. So you just know this is when pixels will show up, this is how much time you multiply it through, and that's your result.
Hello, sorry. I might be right in assuming that the API currently makes the assumption that all rendering happens on the same thread, even in a kind of multi-threaded situation. So like there's assertions in end frame to make sure that it's called on the same thread as begin frame. But in our engine, it doesn't really apply because we have this task-based scheduler where different rendering tasks can happen on various threads. Could we relax that assumption in future updates to the SDK?
So I would want to talk a little bit more what specific issues you are facing with that. We'll obviously need to figure out some way to preempt or generate extra frame data, and that data needs to submit it in timely manner. But around that, I suspect there's ways we can improve things. All right. Oh, okay, last question.
Oh, hi. There are HMD capabilities like available and captured right now in the SDK. I don't think they are used. What is the purpose of those flags, of captured and available?
Can you please repeat what the flags are?
The captured and available HMD capabilities in the SDK right now are not used. What is the purpose of those?
Oh. The captured, I believe those are intended for application transactions. So if you're switching from one to another, there's going to be one which has captured the HMD, and the one which captured will not lose tracking data. But if you decide to switch to a different app, then you let it go. And once it's no longer captured, the mode of tracking can change. So for example, somebody might turn off the camera on you, another app. So you could still read the data, but you don't have control of those settings, tracking settings anymore.
Okay, so I can use this to detect whenever a user changes application, right? That's the goal. Okay.
The idea is you can have 2 applications which access sensor data. And that was actually one of the reasons we separated the logic into a service, is to support those scenarios.
Thank you.
All right. Well, thank you, everyone.